Hello, my dear students. Welcome to IK Sir Chemistry classes. Here we are in lecture number 5 on solid state for chemistry students of class 12. In this video, we will discuss calculation of number of particles per unit cell. The calculation of number of particles, which may be atoms, molecules, or ions, per unit cell in various types of unit cells is very much interesting as well as challenging also. Questions related to it are frequently asked in general and competitive examinations. Let us start our discussion with simple cubic unit cell. The particle present at the vertex of a simple cubic unit cell is common to 8 unit cells as represented in the side-wise diagram. This is a portion of cubic crystal lattice in which this three-dimensional collection of lattice points is repeated several times, and hence this smallest three-dimensional collection of lattice points is nothing but a simple cubic unit cell in which particles are present at all the 8 vertices and particles are not present at any other position in the unit cell. Let us see this particle which is present here. This particle is common to 8 unit cells. This portion of crystal lattice consists of 8 simple cubic unit cells. 1, 2, 3 and 4 unit cells are present in the upper half of the diagram, while 1, 2, 3 and 4 simple cubic unit cells are present in the lower half of the diagram. Thus, this portion of crystal lattice contains overall 8 simple cubic unit cells. This particle, which is present at the vertex of a simple cubic unit cell, is common to all the 8 unit cells. Thus, we can say that the particle present at the vertex of a simple cubic unit cell is common to 8 unit cells. Hence, only 1 by 8th part of a particle is present in 1 unit cell. There are 8 particles present at the vertices of simple cubic unit cell, but only 1 by 8th part of a particle is present in 1 unit cell, as illustrated again in this diagram. This is the particle present at the vertex of a simple cubic unit cell, and it's only 1 by 8th part of this particle of this sphere is present in the unit cell, and accordingly the number of particles present per unit cell in the simple cubic unit cell is equal to 8. It stands for 8 particles present at the vertices, and only 1 by 8th part of a particle is present in 1 unit cell, and hence the number of particles per unit cell will be 8 multiplied by 1 by 8, and it is equal to 1. Obviously, there is only one particle which is present in a simple cubic unit cell. It is quite surprising. According to this figure, it appears that there are 8 particles in the simple cubic unit cell, but it is not true. Actually, only one particle is present in simple cubic unit cell because only 1 by 8th part of a particle present at the vertex is present in one unit cell. Animation representation for the particle present at the vertex of a simple cubic unit cell, which is common to 8 unit cells. It is a simple cubic unit cell. Let us consider this particle which is present at its vertex. This particle is common to 4 unit cells in the same plane. This angle is 90° and 4 such unit cells can be drawn in the same plane. 1, 2 and 3, and initial was 4th. This particle is common to all the 4 unit cells, and 1 unit cell can be drawn over each of these 4 unit cells. And thus, this particle which is present at the vertex of a simple cubic unit cell is common to 8 unit cells, and its only 1 by 8th part is present in 1 unit cell. In fact, the particle present at the vertex of any cubic unit cell is common to 8 unit cells. Let us now consider body-centered cubic BCC unit cell. This is a BCC unit cell in which particles occupy all the 8 vertices. At the same time, the particle is also present at the body center of unit cell, and hence it is nothing but body-centered unit cell. Like in the earlier case, this particle which is present at the vertex of cubic unit cell is common to 8 unit cells. But the particle present at the body center, this one, of a BCC unit cell is not common to other unit cells. This particle is not common to other unit cell. But this particle which is present at the vertex is common to 8 unit cells. This particle which is present at the body center of a BCC unit cell, this particle is totally present in this unit cell and not elsewhere. But the particle, this particle which is present at the vertex of BCC unit cell, its only 1 by 8th part is present in this unit cell, and accordingly the number of particles per unit cell can be calculated as follows: 8 for particles present at the vertices multiplied by 1 by 8, because each particle present at the vertex of a BCC unit cell is common to 8 unit cells, and plus 1, this one for this particle which is present at the body center, which is totally present within this unit cell and it is not common to any other unit cell, and accordingly there are total 2 particles present in BCC unit cell. Now the time for self-assessment. In a cubic crystal, the atoms of element A occupy all the vertices, while the atom of element B occupies the body center of the unit cell. Find out the empirical formula of the compound. In a cubic crystal, atoms of element A occupy all the vertices, while the atom of element B occupies the body center of the unit cell. And thus it is nothing but a body centered cubic unit cell. And now we have to find out the empirical formula of the compound. Now the question arises, what is empirical formula? The chemical formula, which represents the simplest ratio of number of atoms of different elements present in a compound, is called its empirical formula. The chemical formula, which represents the simplest ratio of number of atoms of different elements present in a compound, is called its empirical formula. Let us illustrate it with the following example. Acetic acid. Its rational formula is CH3COOH, which can be transformed into molecular formula as C2H4O2. It means one molecule of acetic acid contains 2 atoms of carbon, 4 atoms of hydrogen, and 2 atoms of oxygen. Thus, the ratio of number of carbon, hydrogen, and oxygen atoms in acetic acid is 2:4:2. But it is not the simplest ratio. It can be transformed into more simpler form, that is 1:2:1, and accordingly the empirical formula of acetic acid is CH2O. CH2O. It means carbon, hydrogen, and oxygen elements are present in acetic acid in 1:2:1 atomic ratio. Now let us solve the given problem. This is the diagram. In accordance with the problem, the atoms of element A occupy all the 8 vertices of the cubic unit cell, while the atom of element B occupies the body center of the unit cell. Number of atoms of element A per unit cell which are present at the vertex can be calculated as earlier. 8 multiplied by 1/8, and it is equal to 1. 8 particles are present at the vertices, and only 1/8th part of a particle is present in one unit cell because it is common to 8 unit cells, and number of atoms of element B per unit cell is only 1, which is present at the body center. Thus, the ratio of number of atoms of elements A and B in the given compound is 1:1, and accordingly the empirical formula of the given compound is AB. It means atoms of elements A and B are present in 1:1 ratio. There is another question for the self-assessment. In a cubic crystal, the atoms of element A occupy the vertices, with one of the vertices left vacant, while the atom of element B occupies the body center of the unit cell. Find out the empirical formula of the compound. The atoms of element A occupy the vertices of the cubic unit cell, with one of the vertices left vacant, while the atom of element B occupies the body center of the cubic unit cell, and we have to find out the empirical formula of the compound. This is the diagram. In accordance with the given problem, the atoms of element A occupy the vertices of cubic unit cell with one of the vertices left vacant, while the atom of element B occupies the body center of the cubic unit cell. Number of atoms of element A per unit cell is equal to 7. 7 particles are present at the vertices, while the eighth vertex is vacant. 7 multiplied by 1 by 8, because only 1 by 8th part of a particle is present in one unit cell, and it is equal to 7 by 8. And number of atoms of element B per unit cell is equal to 1. Ratio of number of atoms of elements A and B in the given compound is 7 by 8 is to 1. But it is not the simplest ratio. For transforming it into simplest ratio, both these terms should be multiplied by 8. And 8 will be cancelled out, and the ratio is 7 is to 8. It is the simplest ratio of number of atoms of elements A and B present in the given compound, and hence the empirical formula of the compound is A7B8. It means elements A and B are present in 7 is to 8 atomic ratio in the given compound. Face-centered cubic unit cell, FCC unit cell. The particle present at the face center of a FCC unit cell is common to two unit cells. It is a FCC unit cell in which all the 8 vertices, 4 above and 4 at the bottom face, 1, 2, 3, 4, all the 8 vertices are occupied by particles. At the same time, the centers of all the 6 faces are also occupied by particles. 6 faces, 1 particle at the center of top face and 1 particle at the center of bottom face, 1 particle at the center of left face, while 1 particle present at the center of right face, 1 particle present at the center of front face, and this particle is present at the center of behind face, rear face. Thus, all the centers of 6 faces are occupied by particles. The particle present at the vertex of cubic unit cell is common to 8 unit cells as explained earlier, but the particle present at the center of face of FCC unit cell is common to 2 unit cells. This particle, which is present at the center of top face, is common to both these unit cells, and hence its only 1 by 2 part is present in this unit cell. Hence only 1 by 2 part of such particle which is present at the face center is present in one unit cell. This is another representation for FCC unit cell. This particle which is present at the vertex of FCC unit cell, its 1 by 8th part is present in this unit cell, but 1 by 2th part of this particle at the center of face is present in the unit cell, and accordingly the number of particles per unit cell can be calculated as follows: 8 multiplied by 1 by 8, since 8 vertices are occupied by particles and only 1 by 8th part of a particle is present in one unit cell, plus 6. 6 particles are present at the centers of faces and only 1 by 2th part of this particle is present in one unit cell, and hence 6 multiplied by 1 by 2. The overall number of particles in FCC unit cell is 4. The number of particles in simple cubic unit cell is 1. In BCC unit cell is 2, while in FCC unit cell the number of particles is 4. Now the time for another self-assessment. In a cubic crystal, the atoms of element A occupy all the vertices, while the atoms of element B occupy the centers of all the faces of the unit cell. Find out the empirical formula of the compound. This is the diagram which has been drawn in accordance with the given problem. The atoms of element A occupy all the 8 vertices, while the atoms of element B occupy the centers of all the 6 faces. The number of atoms of element A per unit cell, 8 multiplied by 1 by 8 is equal to 1, and number of atoms of element B per unit cell is equal to 6. 6 particles are present at face centers, and only 1 by 2 part of this particle is present in one unit cell, and hence 6 multiplied by 1 by 2, it is nothing but 3. The ratio of number of atoms of elements A and B is 1:3. 1:3, and hence the empirical formula of the given compound is AB3. It means elements A and B are present in 1:3 atomic ratio in the given compound. Now let us consider end face centered unit cell. The unit cell in which particles occupy all the vertices and centers of any two opposite or parallel faces is called end face centered unit cell. It is denoted by C. Its diagram is given here. The particles occupy all the 8 vertices of the unit cell, and at the same time particles are also present at the centers of two opposite faces. A particle is present at the center of top face, and another particle is present at the center of bottom face, and these two faces are opposite or parallel to each other, and hence it is nothing but end face centered unit cell. The particle present at the face center is common to two unit cells, and the particle present at the vertex is common to 8 unit cells. Number of particles per unit cell, 8 multiplied by 1 by 8 for the particles present at the vertices, and 2 multiplied by 1 by 2 for the particles present at the centers of opposite faces, and there are overall 2 particles in end face centered unit cell. And now let us consider hexagonal close packed HCP unit cell. The particle present at the vertex of hexagonal close packed unit cell is common to 6 unit cells as illustrated in sidewise diagram. This is a HCP unit cell. This particle is present at its vertex. There are 12 such particles which are present at the vertex 1, 2, 3, 4, 5 and 6 on the top hexagonal face, and 1, 2, 3, 4, 5 and 6 at the bottom hexagonal face. This particle is present at the vertex of HCP unit cell. This angle is 120 degree, and hence this particle is common to 3 HCP unit cells in the same plane. This particle is present in all these 3 HCP unit cells in the same plane, and one unit cell can be drawn over each of these three unit cells. This particle is common to three unit cells in the same plane and three unit cells planes. This particle is common to three HCP unit cells in the same plane and one HCP unit cell can be drawn over each of these three HCP unit cells, and hence the particle present at the vertex of HCP unit cell is common to 6 unit cells. Hence, only 1/6 part of such particle is present in one unit cell. At the same time, the particle present at the center of hexagonal face is common to 2 unit cells, and hence its 1/2 part is present in one unit cell. At the same time, these three particles are present within the HCP unit cell. Accordingly, the number of particles in HCP unit cell can be calculated as follows. There are 12 particles which are present at the vertices of HCP unit cell multiplied by 1/6, because each particle present at the vertex of HCP unit cell is common to 6 unit cells, and hence it will be multiplied by 1/6 plus 2 particles present at the centers of hexagonal faces, and it will be multiplied by 1/2 because it's only 1/2 part is present in one unit cell, and plus 3. These 3 particles are totally present within one HCP unit cells, and hence there are overall 6 particles which are present in one HCP unit cell. Thank you for watching the video with patience. If you find this video helpful and useful to it, please like it, so that inspired from it I may bring more useful videos in future. Please share it to your close friends for their benefit, and if you have not subscribed my channel yet, please subscribe it so that you may get information regarding my new videos in time. Thank you again.